Welcome. In this lesson we're going to be talking about limits and continuity for two variable functions. Our learning goals for today are to be able to describe in words what it means for a limit to exist for a two variable function. We also want to be able to compute limits of continuous functions and to be able to prove that a limit does not exist using graphs, tables, and algebraic methods. Notice that we aren't going to do rigorous proving to show that a limit does exist. That's a topic for 311, an analysis topic. So if you have interest in limits and continuity, be sure to take that class. So to get started, I'm going to start by reviewing what does a limit mean for just a single variable function. This is something that you should be familiar with. Let's say that I'm just in the xy plane and I have some function f of x. And I'm looking at what happens as I approach some x value that's set equal to a. When we were in the single variable case, we looked at right hand and left hand limits. So in this case, the left hand limit as x approaches a is written the limit as x approaches a from the negative side of our function f of x. And in this case, that means that we're approaching a from this direction, and our functional values are getting closer and closer to this circular piece right here. Similarly, our right-hand limit is written the limit as x approaches a from the positive side of our function f of x. And we're looking at as I approach a, as my x's approach a from the positive side, what are my functional values mirroring to one another? And back in this single variable case, we found that a limit is said to exist if the right-hand limit and the left-hand limit both exist and they both agree. I'm not going to write down that they exist, but the idea is that if this limit coming from the left side is equal to the limit coming from the right side, then we say that those limits agree, and the limit value is going to be whatever the value of these limits are. And just as a reminder, it doesn't necessarily mean that our function has to be evaluated at that limit point to be exactly equal to the limit. We still say that the limit exists even if the function might be discontinuous right at that point where that limit is taking place. So now let's talk about what this would mean for a multivariable case. So if you're talking about a multivariable function, and in this case a two-variable function, we no longer can approach just from the right side or the left side. Graphical representations of our functions now are a little more complicated. Let's say that I have some function f of xy, and it's going to look like some sheet out here in three-dimensional space. Here's my x, here's my y, here's my z. And at some point, a, b, out here in 3 space, I want to know, does this limit exist? And similar to what we did with the one variable case, we're going to have to approach it from the right side, and that limit would have to agree with when we approach it from the left side. But there are a lot more sides that I could approach this point at than just the right side and the left side. I could approach my functional output from the left or the right or the top or the bottom. I could even take some crazy squiggly path trying to approach this point. And all of these arrows must converge to the same place in order for the limit to exist. So how can we formally define that in a mathematical way that makes sense? The way that we talk about this is formally is to use an epsilon delta proof. So let's suppose we have a limit L, or a candidate for a limit. And we write this, that the limit as my x, y ordered pairs approach the point a, b, meaning that I'm going to have a whole set of ordered pairs down in the xy plane. and they have to approach my point AB of our function f of xy is equal to L, meaning that our output at AB gives us a limit value of a z value of L if for every epsilon greater than 0, there exists a delta greater than 0 such that for points within delta, maybe I should make this more of a delta looking delta, of AB, we have that the difference between the height at that point, maybe I should label these points, point x, y, star, we have that our L limit point minus our x, y star point is going to be less than our epsilon. Ugh. What does all this mean? Well, you can unpack this in an analysis class. What we're going to talk about is what this picture is representing. Essentially what we're doing, when I pick an epsilon greater than 0, I'm taking some band, some narrow band in the z-axis around my limit value. I probably should use a different color so that I can really highlight this. So once I set up this band, I want to make sure that things aren't jumping outside of this. I want, as I get closer and closer to this f of AB point, as I zoom in on this, I don't want to be jumping outside of this band anymore. And so what this is saying is that I can find some neighborhood around the point AB, so that if I take any point within this neighborhood, here's a candidate point that lives within this neighborhood, and I look at the output, the functional value, the outputs are going to be within this band. So if I live within this delta neighborhood, this is a radius delta, then I'll always have outputs that are within epsilon of this limit. So conceptually, there are two ways to think about limits for two variables. One way to think about limits of two variables is to say that no matter what path I take towards this limit value, all of those paths are converging towards the same place. That's my general way of describing it. A more mathematical way of describing it is saying, once I take a narrow band around my potential limit value, L, I know that I can find some narrow neighborhood around my original point AB such that my outputs will always lie within that band. So that's the theory for today. Hopefully that's not too much theory. Let's step away from theory and talk about what are some properties of limits, and then move into continuity and calculating limits. So properties of limits, I have conveniently already written out for us as limit laws on this board because I didn't want to write them all out. The reason why is they're all exactly what you think that they might be. So our limit laws are saying, assume that I have limits that exist. So if my function f of xy approaches AB, this limit exists, and this limit also exists, meaning all of those paths that are zooming in on that point all go the same flips to the same place. What does that mean? Then a bunch of things that you think should be true actually are true. The sum law says that the sum of those two limits is going to be the limit of the sum. So if I have my point my point xy and R2 approaching some point AB, my outputs added together will be the limits of each of those outputs added together. Constant multiples also hold, so that means that if I take the limit of some constant times my function f, I can pull that constant outside of the limit. This is exactly the limit laws that you saw in single variable functions. We also have a product law, that if I'm taking the limit of the product of two different functions, that's going to be the limit of the products. And finally, our quotient law is that the limit of a quotient is going to be equal to the quotient of the two limits, assuming that the limit as xy approaches ab of g, so whatever's in the denominator, that denominator limit is not equal to 0. That's what the little star is telling us. So we can take this quotient so long as it's defined, and if this denominator is 0, then it wouldn't work out. I don't want to spend a lot of time having you memorize these, because these really are intuitively what they think that they might be. But we're going to do a couple of examples now where we're going to use and evaluate limits. Nope, I lied. Before that, I want to introduce the definition of continuity. It's exactly what you think it might be based on your understanding of continuity from the single variable case. So we say a function f of xy is continuous at a point a, b, if the limit as xy approaches ab of my function f of xy is exactly equal to what you want it to be, the function evaluated at that point. So that means that as I take all of these different paths that are zooming in to this point AB, I want to make sure that they're actually zooming into the right place, that my limit is exactly equal to whatever the function value is right at that point AB. So a way to visualize any continuous function that's a two-variable function is going to be some type of continuous sheet. There aren't going to be rips, there aren't going to be holes, you aren't going to have gaps. This continuous sheet could be curvy in lots of crazy curvy ways, but it'll be continuous, right? No holes in it. The reason why that's nice is that continuous functions are easy to be able to take limits of. And now I'll do a couple of examples. So my first example, let's take a look at